Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over question number 4 of the 2017 AP Calculus free response question. In this presentation, we're going to be taking a look at how to use the tangent lines to approximate functions and how to solve differential equations using the method of separation of variables. Alrighty, let's take a look at question number 4, the A part. In 4A, we're going to be looking at how to approximate functions using the tangent lines, okay? Question 4 reads, at time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius at time t equals 0. And the internal temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies this differential equation right here, where h of t is measured in degrees Celsius and h of 0 is 91. Question, part A. Write an equation for the line tangent to the graph of h at t equals 0. And then use this equation to approximate the internal temperature of the potato at time t equals 0. Alright, to get us started, we're going to outline our plan of attack for this problem. Alright, so let's see how we're going to solve this problem. So our plan is as follows. First of all, we're going to find the equation of the tangent line. Okay, find the equation of the tangent line. Now the form that we find the equation of the tangent line is important. We're going to find the equation of the tangent line in the y equals mx plus b, or the slope-intercept form. Alrighty, well, why is that? Well, if we have it in slope-intercept form, it will be possible for us to carry out the next part, which is to evaluate the function at the specified approximation value. Alright, so for part 2, we're going to plug 3 into the equation to approximate the temperature. Okay, plug 3 into the equation from 1 to approximate the temperature. Alrighty. Okay, so now let's go ahead and write down the relevant formulas that will guide our problem solving process in this example. Alrighty, so the first formula that we need is the formula for the equation of a tangent line. Alright, so the equation of a tan line, also referred to as EOT, equation of the tangent line, can be found using the formula y minus y1 equals m times x minus x1. This is the point slope form of the equation of a line, okay? And then when you get y isolated, you have y of your equation of tangent line is equal to mx plus b. And with this form, you can basically use this as an approximator of points in a function, okay? The closer you are to the point of tangency, the more accurate this approximator is. Alrighty? Okay. And then part 2, we're going to if you want to approximate the function, so you can basically approximate a function, approximation of f of a can be done using the equation of the tangent line, okay? Y EOT at that value that you're estimating, okay? Some textbooks make use of the terminology linearization. So the idea is that the closer you are to the point of tangency, you have a greater similarity between the function itself and the tangent line. Alrighty? Okay, now let's go ahead and get started. Number 1. Part 1, we're going to find the equation of the tangent line at the specified point at t equals 0. So what we're given in the problem, we're told that h of 0 is 91. All right, so we know that we know that h of 0 is 91. Now, in some problems you have y and x. In this problem we have h and t, so you just need to know what your dependent and independent variables are. In this particular case, the independent variable is the t and the dependent variable is our h. So if we want to adapt it to this problem, our x1 will be our independent variable, which is 0, and then y1 will be the dependent variable, which is h, and that is 91. Okay, all right, now we also need to find the slope. M is basically the derivative at the point of tangency. Okay, so h prime of 0, or the derivative of h with respect to time evaluated at the point 0, 91. So this is kind of a strange problem. For this particular problem, you just have to know that the x component is 0, or the t component is 0, and the y or the h component is 91. Alrighty, so you want to keep track of your values, what your values signify, so you don't mess it up when you're carrying out your substitution. So what we're going to do now is find m. M is still a mystery because we need to look at the value of the derivative at 0. So m is h prime of 0, and so we're just going to plug in the appropriate value into our function. So what do we know about dh dt? dh dt is negative 1 over 4 h minus 27. So it's going to be negative 1 over 4 times h minus. Now you got to be careful here. At 0, we're plugging in this derivative is dependent on h. Okay, so we're going to be plugging in h into this function right here. So instead of, it's not 0, we're going to be plugging in the h value, which is 91. 91 minus 27. Okay, because the derivative or the slope is dependent on h, not t. So let me just put that somewhere here so you can see. We have the h dt, so the derivative is negative 1/4 h minus 27. So it's the y value or the h value that gets plugged into the differential equation in order to get what the slope is. Okay, all right, so be careful with that. Always pay attention to what you're substituting into your slope equation. We'll simplify this. We have negative 1/4 times 64, and that gives us negative 16. So that's the slope of the tangent line. So put everything together in the point slope form of the equation of the line. Let's rewrite the formula again so we don't get confused. Y minus y1 equals mx minus x1. All right, so if we substitute, we're going to have y minus y1, what is y1, 91, equals m, the slope we just got, negative 16, x minus x1, what is x1, 0. Okay, so this is the point slope form of the equation of the tangent line, but we need the slope intercept form. Why do we need the slope intercept form? Well, in order for us to carry out the approximation, we need to be able to substitute, we need y by itself, so we can just substitute the t value in there and basically be done with the problem, okay? In this format, it takes too much work to do that. So what we're gonna do now is we're gonna place in y equals mx plus b form. In this particular problem, it's gonna be mt plus b, because our independent variable is t. Alrighty, so we have y minus 91 equals negative 16 times x minus 0. So just get y by itself. So you have y minus 91, distribute negative 16 equals negative 16t, and then you add 91 to both sides, and you have y equals negative 16 plus 91, or using the, negative 16x plus 91. Or using the independent variable that we're working with here, we can just write it as y equals negative 16t plus 91. Okay, So now this is the equation of the tangent line. This is what we're going to use as our approximator. Okay, so h of 3 can be approximated using the equation of the tangent line evaluated at that value, which is 3. So just basically plug in what you're approximating into the equation of your tangent line, and then you're going to have negative 16 times 3 plus 91, and that's negative 48 plus 91. And then if you work that out, your final answer is going to be 43. Okay, so this slope-intercept form of the equation of the line is our approximator. All right, so that's that. All right, so on the AP exam, this particular problem was a three-pointer. It was a 3-point problem. You get 1 point for getting the slope correctly. Where was the slope? Negative 16. You get 1 point for that. You get another point for getting the equation of the tangent line. And then you have another point for using the equation of the tangent line to approximate the function, for a total of 3 points for 4A. Alrighty, let's take a look at question 4B. Question 4B, and this one we're going to be looking at how higher order derivatives, namely the second derivative, can give us some important information concerning the accuracy of an estimation, if it's an overestimation or underestimation relative to the actual function. So question 4B reads, use the square h dt squared to determine whether your answer in part A is an underestimate or an overestimate of the function at time t equals 0. Okay, so let's go ahead and specify what the differential equation was from part A. We had the h dt. The h dt equals negative 1/4 h minus 27. All right, so this is the differential equation that we're talking about right here. All right, so what's our plan of attack here to determine if the answer we got in part A was an over or underestimate? In part A, we basically found the equation of the tangent line, so we want to see how does it compare to the actual value of the function. All right, so let's go ahead and specify our plan of attack. First of all, we are going to find the second derivative of h of t, starting from the first derivative. Find the second derivative of h of t, and then what we're going to do is we're going to use the concavity. It's all about the concavity. Okay, we're going to use the concavity to compare the estimation. Okay, to compare the estimation to the actual. Is it over or under? The concavity can tell us exactly what we need to know concerning that. Alrighty? Okay, so let's start with the first part. First part, we're to find the second derivative of h with respect to t, d square h dt square. Alright, so let's go ahead and start. We're going to be starting from dh dt. Now, whenever you're differentiating, you always want to pay attention to what you are differentiating with respect to. Now, if you have a situation where only the independent variables on the right side, then you don't have to bother too much. But in this particular function right here, guess what? We have an anomalous situation. We have the dependent variable on the left side. Okay, so that means you have to pay special attention. We are differentiating with respect to t, so this is kind of sort of like implicit differentiation since it's not explicit in terms of h, because we have h on the right and we have h on the left. Okay, all right, so let's go ahead and differentiate that. So the derivative, the second derivative of the function, d square h dt square, is, we're going to differentiate this right here. So we have 1/4. What we can do, let's let's do this. How about before we differentiate, let's just distribute the 1/4 in there first so it doesn't look strange and kind of confusing. Um, so we have the h dt is equal to -1/4h. Minus times minus is plus 27/4. Okay, all right, let's go ahead and differentiate. The square h dt square. Now, this is a mistake most students will make when they differentiate on the right side. They'll say, oh, it's just -1/4 as the derivative. No, that's not correct. But what's wrong? Well, we're differentiating with respect to h, so we have a disagreement here. All right, so it's going to be, you factor out the -1/4. The derivative of h is 1, but since you have a disagreement with respect to what you're differentiating with respect to, you have to add on the h dt. It's kind of like implicit differentiation. Had it been -1/4 t, then it would just be -1/4 as your derivative. So be really careful when you're carrying out higher order derivatives. Pay attention to scenarios where you have to use implicit differentiation. Okay, so let's make that look pretty. The second derivative, the square h dt square, is -1/4. Now dh dt. Now to finish this off, we have to substitute what dh dt is. We don't want to forget that. So we're going to substitute, what are we going to do? We're going to substitute -1/4 times the quantity h minus 27 for dh dt. Okay, so let's carry out the substitution. That will give us exactly what we need. So we have d square h dt square is equal to -1/4 times the h dt is now, just take this value and plug it in here. So let's put the brackets. It's going to be bracket -1/4 times the quantity h minus 27, like that. Okay, and then if it distributes, we have the second derivative, the square h dt square is equal to negative, or actually that becomes a positive, so it becomes 1/16 times h minus 27. Okay, all right, so there goes the second derivative. Now, is based on this second derivative, is it an over or under estimate? Okay, so in order to do this, we're going to use our fun chart. Well, in this particular one, we're going to use our Hunt chart here. So let's take a look at that. So you have the function h, concave up, down, h prime, increasing, decreasing, h double prime, positive, negative, increasing, decreasing, positive, negative. Okay, so if the second derivative is positive, the function is going to be concave up, okay? And if the second derivative is negative, the function will be concave down. Now, what is the significance of that? All right, this is very important. You need to remember, recall that if the second derivative is positive, let's say greater than 0, the function is going to be concave up, okay? So the function is concave up. Where does the tangent line sit? The tangent line will sit beneath the function, regardless of where you place it. So if you have a concave up scenario, your tangent line approximation will be an underestimate. Okay? And then if your second derivative is negative, you have a downward or a downward facing concavity. How does that impact the tangent line? Well, the tangent line is always going to be above the function, all right? Which basically means your tan line approximation will be an overestimate. All right, so all we just need to know now is this second derivative positive or negative? And then we'll be good to go, all right? So d square h dt square, we know that, well, 1/16 is positive, right? But how about h minus 27? Well, originally in the problem, we were told that h is greater than 27 for all t greater than 27. Okay, so h is greater than 27, so we have positive times h minus 27. So since it's stated in the problem, since h is always greater than 27, what does that mean? The difference between h and 27 is going to be positive. It's going to be greater than 0. Okay, for example, h could be 28, so 28 minus 27 is positive 1. So since h is always greater than 27, this difference will be positive. So the second derivative is going to be positive times positive, which is positive. Okay, so what does that tell us about the concavity? It tells us that the function is concave up, and if the function is concave up, that automatically follows that your estimation is going to be an underestimate. Okay, so let's go ahead and write down our reasoning explanation. Since d square h dt square is positive, let's write it out. It's positive. H is concave up, which makes our tan line approximation what? If it's concave up, our tangent line approximation will be underneath, as indicated here. Okay, it's going to be underneath the function always for upward facing concavity. So a tangent line approximation will be an underestimate. Okay, so that's that. All right, so question. How many points do you think you get for all this work? You get exactly 1 point. Okay, you get 1 point for this problem on the AP exam. Alrighty, let's go ahead and take a look at question number 4C. In question 4C, we're going to be assessed on how to solve differential equations using the method of separation of variables and using our particular solution to evaluate basically the function at a particular time. Alrighty. Question 4C reads, for time t less than 10, an alternate model for the internal temperature of the potato at time t minutes is a function g that satisfies the differential equation dg dt equals negative quantity g minus 27 to the 2/3, where g of t is measured in degrees Celsius and g of 0 is 91. Find an expression for g of t. And then based on this model, what is the internal temperature of the potato at time t equals 0? Okay, so let's go ahead and write down our plan of attack here. So you have to remember that differential equation problems normally pack a lot of points on the AP exam, normally the most points. So it's important that you know how to solve your differential equations for the AP Calc exam. All right, so plan. Since we're solving using separation of variables, we're gonna use sci-fi here to solve the differential equation. And then after we solve the differential equation, we don't want to forget the second part. We're gonna evaluate the particular solution at t equals 3. Okay, so evaluate the particular solution, which is the final answer you get from the first part, at t equals 3. Okay, all right, so let's go ahead and get started. So in sci-fi, we know the steps that we're going to be using to solve our differential equations. In sci-fi part 1, we're going to separate. Okay, so separate. In this particular problem, we have two functions, function of g and a function of t. So we're going to have the g's on the left. Okay, so f of g and dg, they're going to be on the left side. Let's try that again. Function of g and dg will be on the left. And then we'll have f of t and dt on the right. Okay, so that's basically how we're going to separate our variables. Okay, so what is f of g and f of t and all that in this particular problem? Let's specify what they are. Give me a second. Let me split this up down the center. Okay, so in this particular problem, if you look at the differential equation that we're trying to solve, this one right here, f of g, the function of g, is negative. Let's leave the negative out of it. So f of g is quantity g minus 27 raised to the 2/3. Okay, and then the function of t, f of t, is just going to be -1 in this particular case. So we're going to separate it like that. So this whole piece will be on the left side, and then this will be on the right side, and then dg will be on the left, and then dt will be on the right. Okay, so let me show you exactly what I'm talking about. So we have dg dt equals negative quantity g minus 27 to the 2/3. Okay, so dt needs to go to the right side, so we'll multiply both sides by dt. What we're doing right now is a process called separation of variables. Okay, all right, so if we do that move, the dt's divide out on the left side, and then we have dg is equal to negative quantity g minus 27 raised to the 2/3 dt. Okay, now we need to move this function of g to the left side of the equation. To accomplish that, we're going to multiply by 1 over g minus 27 to the 2/3, or just divide by that, the same thing. Okay, all right, so multiply that on both sides. The quantity g minus 27. All right, so on the right side, these quantities divide out. Okay, and then we have a separated differential equation, 1 over g minus 27 to the 2/3 dg. Okay, so this is f of g and dg on the left, and on the right side we have f of t, which is -1 dt. Okay, so we have separated the differential equation, separated. So we've accomplished step S in our sci-fi process. Now what we're going to do next is we're going to get rid of this dg and dt business by integrating. Okay, so think about dg and dt as differentials, and the reversal of that is integration. Okay, so let's specify what we're going to do. So for part 2, we're going to integrate. That's the I in sci-fi. Integrate both sides. The goal here is to eliminate the differentials. So we have the integral of 1 over quantity g minus 27 to the 2/3 dg equals the integral of -1 dt. The right side is a piece of cake to integrate. The left side requires more work. So what we're going to do is, I would like to integrate them at exactly the same time. Okay, so I'm just going to keep this one the way it is, and then deal with this problem on the left. Now if you take a look at the integral on the left side, we have a composite function, and the derivative of an inner function, g minus 27, is a multiple of dg, basically times 1. Okay, so what method of integration are we to use here? The u substitution method. Okay, so in this particular case, u is going to be g minus 27, and then when you differentiate that, du is going to be dg, and this is a perfect substitution case. We don't have to do any manipulations because it fits perfectly. What does that mean by it fits perfectly? Well, check this out. If we call this u, okay, this dg is du. Sometimes we have to do some algebraic manipulation to let it work, but in this case we don't have to do that, which is fantastic. So we're going to now rewrite our integral with the u substitution. This becomes the integral of 1 over u to the 2/3 du is equal to the integral of, let's put a minus here, minus 1 dt. Okay, now how do we integrate this? Well, if I can write this as a power, then I can just use the power rule for integration to do it, okay? So if I want to rewrite this as a power, I will have to make use of the reciprocal property of exponents. So let's specify exactly what we're about to do first, and then we'll do it, okay? So we're going to rewrite as a power. So we can use the power rule. All right, so if we rewrite as a power, we're going to have the integral of u to the negative 2/3 du equals negative integral of 1 dt. Okay, ladies and gentlemen, we are now ready to integrate. Oh, before we're ready to integrate. So let's go ahead and do that. So if we integrate the left side, we apply the power rule. What are we going to get? If we apply the power rule to the left side, we're going to have u to the power plus 1, which is 3 over 3, divided by the power plus 1, which is 3 over 3. And if we integrate 1, you just have t, so negative t. There was a negative there before. And then this c is a combination of the c's from both sides. Okay? All right, let's simplify. We're going to have u to the 1/3 over 1/3 equals negative t plus c. Okay, and then we can drop, change, flip, so this becomes 3. Now we have to resub. Don't forget to resub what u is. U is, what is u? G minus 27. So it's g minus 27 to the 1/3 equals negative t plus c. Okay, please don't forget the resub step, because if you don't do the resub, your next step, which is to find c, will be incorrect. Okay, so we're going to resub right here, and now we're going to advance to part 3 in sci-fi, which is to find c. You find c using the initial condition. Okay, using the initial condition, which is g of 0 equals 91. That was provided to us here. Oh, where'd it go? Oh my goodness. Okay, so g of 0 equals 91. It was provided to us here, so that's what we're going to be using right here, okay? So what does this mean? It just simply means we're going to substitute t for 0. 0 for t, okay? And then substitute 91 for g, and then solve this equation for the resulting c value. Okay, so let's do it. So we have 3 times, instead of g, we replace it with 91 minus 27 raised to the 1/3 equals negative t is 0, plus c. Okay, let's simplify this. 3 times 91 minus 27 is 64 to the 1/3 equals c. The third root of 64 to the 1/3 is just a cube root of 64, which is 4. Okay, so 3 times 4. Okay, so we now see that c is equal to 12. Okay, and then the last step is to find, isolate y. In sci-fi, we're going to isolate y, okay? Y is the dependent variable in the sci-fi formula, but in this particular problem, the dependent variable is g. So to get a particular solution, we have to isolate g here, okay? But is y in other cases if it's a function of y. All right, so let's go ahead and isolate g. So to get us started, we're going to have to put in 12 into this equation right here. So we have 3 times the quantity g minus 27 to the 1/3 equals negative t plus 12. Okay, so this right here is the implicit form of the particular solution. Over here, let me just specify something, just a side note. This solution that we came up with over here is the general implicit solution. What we're looking for is a particular explicit solution. So this is the general, this is the particular implicit solution. So if we want to get it in the explicit form, we need to get G isolated. Okay? All right, so this is the particular implicit solution. And then what we have up there is the general implicit solution. General in the sense that we don't know what C is, okay? It's a general case, but this is particular because we are fixing our solution to this particular C value. All right, so to get the particular explicit solution, which will enable us to do the last part, we're going to have to get G isolated. Okay, so it's just algebra from here. So we're just going to divide by 3, take the third power, and add 27. Okay, all right, let's do it. So just divide both sides by 3. And then you have the quantity G minus 27 raised to the 1/3 is equal to negative t plus 12 over 3. And then the inverse of the third root is the third power. So raise both sides to the third power. Write that again. So raise both sides to the third power. Okay, so that gets rid of that. And then we have G minus 27 equals the quantity negative t plus 12 over 3 to the third. And then you proceed to add 27 to both sides. And then you have G of t is equal to the quantity negative t plus 12 over 3 to the third plus 27. Ladies and gentlemen, this is exactly what we're looking for. Bullseye right here. This is the particular explicit solution. How do you know you've achieved the particular explicit solution? If you have the dependent variable, namely G, in this case isolated, and there are no C's present, then you know that you've achieved the particular solution in explicit form. Okay? All right, so in some problems you're done, but in this particular problem, we're asked to use our solution to do something, which I forgot already. Let's see what it said to do. It says, based on this model that we just found, G of t, what is the internal temperature of the potato at time t equals 3? Okay, so all we're just going to do now is just evaluate G of t at t equals 3. So let's specify that. Evaluate G of t at t equals 3. So what we're looking for is just G of 3, okay? So G of 3 is the quantity negative 3 plus 12 over 3 to the third power plus 27. Okay? So for the AP exam, you can leave it just like this. That's sufficient, but we're just going to go all the way. We're just going to use our order of operations here to finish up the problem. So we have negative 3 plus 12 is 9. 9 over 3. Cubed plus 27. 9 over 3 is 3. 3 cubed plus 27 is 27 plus 27. And our final answer is 54. Okay, so the internal temperature at t equals 3 is 54 degrees Celsius. And there you have it. Okay, so how was this problem graded on the AP exam? Well, as indicated earlier, we stated that differential equation problems pack a lot of points. So this particular problem was worth 5 points, which is a lot. Out of the 9 points, this is 5 out of 9. Okay, so how was it graded? Now you get, let's see, by separation of variables, you get 1 point. If you integrate correctly all the way here, you get another point. And then if you use, just by using the initial condition to find C, so you use the initial condition g of 0 equals 91 to find C, that gets you another point, right? So you have 3 points so far. Now if you get the final solution g of t, the particular explicit solution, you have another point right here. And then scroll down, you have another point right here. And then when you finish it off by using g of t and g of 3, you put it together to get 54, you get your final point for a total of 5 points. Okay, so that's how this problem was graded. Thanks so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming AP exam, do give us a like or thumbs up. Your positive feedback is extremely valuable to us. If you have any questions or comments about what we covered, or any special requests about the AP Calculus exam in general, just place your questions in the comment section below and we'll be more than glad to respond. Don't forget to subscribe to our channel for updates to future uploads. We upload videos to our page on a weekly basis. For more support resources, visit our website at mathgotserved.com or take a look at the link in the descriptions below. Thanks again for watching and have a wonderful day. Goodbye.